Okay, we started recording. Let me start to share my screen. Just a moment. Okay. Okay. So, I share with you exercise about soil classification, and I ask you to classify 3 soil profiles.
Yes.
Try to classify the surface diagnostic horizon, and for some of them, the subsurface diagnostic horizon too. And this first exercise, we have 5 horizons. And I just ask you to classify the surface diagnostic horizon. Okay, so you don't need to worry about the second and below, but the first one, it's quite important to us. And let's see the morphology of this horizon. It has 45 centimeters of thickness. The color is N2.5. That means that it possesses a gray color. Okay, this symbol, this N, means neutral or without hue. So the soil of this horizon is not red, it's not yellow or green or a mix of these colors, but present a gray color. Okay, this and all of these horizons present this N page, so means that it not possess a hue or not possess a red or green or yellow color. Okay, it's quite important to us for the identification of the surface diagnostic horizon in this example. The texture of this horizon is sandy clay loam. Okay, so present a higher content of sand, we can see here, but present a high content of clay or even higher than 15%. And because we have a mix of sand and clay, we have a sandy clay lawn. Okay. The structure presents a strong grade, so it present a strong development, and the size of these pads, of these aggregates, it's coarse, so the pads are coarse, and these pads presents a granular type, so present our circular shape. Okay, that's quite related to soils or horizons that present a high content of organic carbon. The organic carbon we can see here, that's quite high. It's 28%, 22%, 15%. So this first 2 horizons, especially the first one, the surface horizon, it's quite high. The consistency of the horizon is very hard when dry, firm when moist, and present oh, I'm sorry, I think that something wrong here, because clay, it's not, shouldn't be here. Here we should present the consistency of this material when wet. So we don't have this information, but it's not important to us. I have to correct this. We don't have this clay, this word here, okay? But okay, what we need to understand here, that this surface horizon presents an acidic pH, a low pH, and a high content of organic carbon. Let's see which surface diagnostic horizon we have in this example. Again, we have several. Let me just see. I think that someone. Okay, let me just turn off the microphone. Okay. Okay, so we have some surface diagnostic horizons, and the folic and histic are those organic horizons that present a high content of organic carbon, or at least equal or higher than 20%. That is the case. So to identify a folic horizon, we should present organic material that has organic carbon content equal or higher than 20%, but this horizon is formed only in environments, in sites that we don't have several days with saturation, with soil saturated, or with influence of water table or tidal water or something like that. So because we have this neutral color, this N2.5, we have in this case a high number of days with influence of water, because we don't have a red or yellow colors. We have a gray color, and gray color, it's only formed when we have a soil or a horizon that's influenced by water table, tidal water, or something that avoid the penetration, the conductivity of water. So in this case, we can't, or we shouldn't classify this surface horizon as a folic horizon, okay? Because it did not present a few days or a low number of days with soil in soil moisture that represent a high content of water. But we have the histic horizons, and the histic horizon is those horizons that present a high content of organic carbon, as I said, equal or at least 20%. So if we check here the data, we have a high content of organic carbon. So, okay, it could be a histic horizon, and the histic horizon should present a high number of days with soil flooded or influenced by water. So if we compare the color, the N color, the absence of hue, we can understand that this first horizon presents a high content of organic carbon, and at the same time present a high number of days which is influenced by water. And the last criteria is that the histic horizon possesses a thickness equal or higher than 10 centimeters. And in this first exercise, we have a horizon that possesses 45 centimeters of thickness. So all the criteria that identify a histic horizon are followed. So in this case, we have a histic horizon because we have a high content of organic carbon, and because we have a neutral color that indicates, oh, just a moment, someone's asking. Okay. So in this case, in this exercise, we have a histic horizon because, first of all, we have a high content of soil organic carbon. Second, we have a neutral color. We have a gray color that indicates water table influence or tidal water influence. And we have a thickness higher, equal or higher than 10 centimeters. So this first exercise, the surface diagnostic horizon, is a HISTIC horizon. This is quite important because identifying the HISTIC horizon in this exercise, we could classify the soil, and in the next week, we start to classify soils according the diagnostic horizons that we could identify, okay? So this first exercise, we possess a HISTIC horizon. The second exercise, I ask you all to classify the surface and subsurface diagnostic horizons. So let's check. The first horizon is an A horizon, so it's a mineral horizon. The soil organic carbon, it's lower than 20%, and we can see here is just 3.5%. It's not an organic horizon. It's not an H or O horizon. And this A horizon possesses 15 centimeters of thickness. So it's not so thick, but it's not so sharp too. We have a color that is 7.5 YR. So in this case, this horizon, it's redder or yellow. We can see a red color here or a yellow color. What do you say? What do you think about the color of this first horizon? Using the hue.
It means it is let me see, 7.5.
Yes,
That's
but
that is 7.5 yellow, 2.5 red.
it means that it's more red
Yellow.
or more
Yes,
yellow. Oh, yes, yes, it's yellow.
more
You
of
just
yellow.
need to,
Yes.
Oh,
yes,
JJ is more yellow.
yes, yes, it's more yellow. You can see that this number, it changed, it varies between 0 and 10. So in this case, we have more yellow and just a few contribution of red spectrum. So we have a yellow horizon. The value and the chroma are low because they are equal or lower than 3. So it's a dark yellow or brown yellow in this case. This dark color is related to the incorporation of organic matter and melanization of the mineral material. And the texture is classified as clay. So the clay content is high, and we can see here that we have 62% of clay. That's quite high, okay? The structure is classified as strong, coarse, granular. So the grade is strong. So it possesses a strong development. It possesses a coarse size. So the pads presents a coarse size, and they possess granular shape, a granular type. So they are related through incorporation of organic matter, okay? And granular shape is generally related to intense bioturbation. As we can see here, evidence of bioturbation in this specific A horizon, okay? It possesses a consistence of classified as soft, when dry, very friable when moist, hard and firm. Oh, hard and firm. Yes, yes. I think that something is wrong here again. Sorry. It couldn't be verifiable and hard at the same time, and even firm. I think that I just forgot to erase this. Just a moment. Okay. 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 But it's not a problem. Again, this is not a problem. It possesses a consistency when moist that's slightly plastic and slightly stick, and a transition that's smooth and clear. Okay, so this first horizon presents 15 centimeters of thickness, a brown yellow color or a dark yellow color, a high content of clay, and it possesses a strong development, okay, with a structure that reveals high activity of termites, of ants, of wormholes, or and other animals.
I'm
Um,
sorry, JJ.
yes, yes, what?
Yes. So it means for this one, we will remove the very friable part and remain with the hard and firm since it's a clay.
Yeah, yeah. Maybe I should choose one of this. It could possess the all this information. Just two of them, or soft or hard. It couldn't be soft and hard at the same time, and it couldn't be
Okay.
very friable and firm at the same time.
And firm.
So
Okay.
maybe it's just soft and very friable and slightly plastic and slightly stick. Okay,
Mm-hmm.
like here is correct, and here is correct, and here is correct. So the BA horizon, B1 and B2, they are correct, but this first horizon, I made some mistakes. So, okay, in this case, I forgot to raise information. Maybe hard and firm are the wrong answer here, but it's not a problem because it did not influence the classification in this case and the most of the examples. Okay.
Okay. Thank you.
Okay, welcome, welcome. So let's see which horizon this surface horizon is. It's not folic and histic horizon because the folic and histic horizon, they are related to organic materials, so they should present organic carbon content equal or higher than 20%. And in this example, we have only 3.5%. So the content of, oh, and here in this case, it's soil organic matter, and we need to calculate the content of soil organic carbon. How can we calculate the content of soil organic carbon? It's quite easy. We just need to divide this number, that is the content of soil organic matter, by 1.741. So in this case, we have 3.58% of soil organic matter. And to calculate the content of soil organic carbon, we just need to divide it by 1.741. So the content of our soil organic carbon in this first horizon, in the surface horizon, is just 2.05. So it's lower than this. because the
Hello,
organic
JJ.
matter content, it's always higher than organic carbon content.
Hello,
Okay,
JJ.
yes,
I
yes.
think the conversion ratio from organic matter to organic carbon is 1.724, not
It
1.714.
one dot what?
1.724.
724?
Yeah, I guess so.
Um, I'm not sure. Yeah, let me check. Just a moment, okay? Oh, oh, I'm quite sure that. Oh, yes, yes, I'm sorry. Okay, just a moment. Let me share my screen with you. Okay, just a moment. It's right. Yes, yes. It's just 1.724. I'm sorry. I'm showing here just this. So the value is quite close, but it's not the same. So let's use the right number. Just okay. Okay, okay. So it's 3.58. Let me correct that and divide it by 1.724. Now I'm using the right number. Okay, it's just 2.07. That's quite similar, but it's right. We should use the right factor. So we have only 2% of soil organic carbon in the surface horizon. So the organic carbon, it's quite low and it's not a folic or haystack horizon, okay? So let's see which surface horizon could be. It's not a folic, it's not a haystack, anthratic. It should present fluid conditions and should be mixed by humans. So it could present a low value and a low chroma. Okay, we have low value and low chroma. It should present a platy structure or a massive structure, and we did not present this. Okay, so it's not an anthratic horizon, a Arctic horizon. It should present a low value and a low chroma. Okay, we have a low value and a low chroma. Let's see here. We have a value of 3 and a chroma equal to 2. Okay, it should present or soil organic carbon equal or higher than 1%, and we have 2%, so okay. We should present a content of phosphorus that's equal or higher than 120. And here we have, let's see, 115. So we have a phosphorus content that could be related to a Arctic horizon. It should present a base saturation equal or higher than half of the cationic exchange capacity. So let's see, in this case, we could calculate the cationic exchange capacity just summing the calcium, magnesium, hydrogen plus aluminum, and potassium contents. And in this case, we just need to do this. 5.34 plus 0.2 plus 3. Okay, it's just 8 5.54, but we have to consider the content of potassium in this case, and we should pay attention that in this specific case, the potassium content possess a different unit from the rest of these cations, so we should convert this content milligrams per decimeter to centimole charge by decimeters. So in this case, we just need to convert this data using the molarity of potassium. To convert this, let me just type this number so I didn't forget this. Just a moment. To convert this, I just need to divide the content of potassium by 390. So the content of potassium in this case, in the surface diagnostic horizon, is just 0.12. It's quite low. So 8 plus 0.12, it's just 866. So it's a low value. Okay. And now I need to divide the number, the content of all the bases, that's potassium, sodium, calcium, and manganese, magnesium, by the all negative charge that we have. So in this case, I just need to sum potassium, that's 0.12, plus, we don't have sodium, we have calcium, it's 5.34, and we have magnesium, again, 0.2. So we have a sum of bases that equal to 5.666. So if we divide this number by all negative charges that we have and multiply this per 100, we have 65% of negative charges that are fulfilled by bases. So we have a base saturation that's equal or higher than 50, because 65 is higher than the half. So we follow this criteria too. We should process exposed area of at least 25% of evidence of animals, or evidence of bioturbation, like animal pores, tubular or dendritic tubular pores, coprolites, and other traces of soil animal activity. In this case, this horizon possesses an abundant evidence of perturbation, so it also follows this criteria. And the last one, it's a thickness equal or higher than 20 centimeters. So in this case, we have 20 centimeters. So in this specific case, in this exercise, we have a Arctic horizon in the surface of the soil. So just raise this. The horizon is a Arctic horizon, okay? And now we should classify the subsurface horizon. That's B2, B1, and this transitional horizon, okay? They are the master horizons, in this case, B2 and B1, and Here we have the transitional horizon. And we have some information that's quite important to understand, to calculate when we should classify the subsurface diagnostic. And one of them is the organic carbon content, and if we can register a significant clay increase in subsurface. So let's see, the soil organic carbon here should be very low because the B2 and B1 horizon possess equal or lower than 1%. So of course, these horizons, they did not are folic or histec horizons. They are mineral horizons, okay? And in this case, we should now calculate the increase of clay. In this case, we have 7% of clay in the B1 and B2 horizons, and the content of clay in A horizon is 62. So we have a slightly increase of clay, but we should know if the increase it's an high enough to identify our argillic horizon. Okay, so let's see if we have more equal or more than 50% of clay in a surface horizon, in an under overlaying horizon, we should present at least 20% more clay in the subsurface horizon. So in this case, we have 62, and to identify an argillic horizon, we should possess at least 82% of clay, or we should present shiny surfaces. We don't have any description of shiny surfaces in B1 and B2 horizon, or even in BA horizon, this transitional horizon. So we don't have shiny surfaces, and probably we don't have an argillic horizon, but we also can calculate the clay increase. And in this case, the clay increase is not high enough to identify an argillic horizon. So the subsurface horizon is not an argillic horizon. Let's see other horizons that could be related. Just a moment. Okay. Here it's just a surface, 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 just a surface. Oh, this could be a surface or a subsurface, but it's related to accumulation of secondary gypsum. So we should present an increase of sulfate, calcium sulfate. Let's see if we have a high content of calcium. No, we have a low content of calcium. So it is not probably a horizon that could present a high content of calcium sulfate. Salic horizon that possess a high content of soluble salts. In this case, we should present a high pH and or a high electric conductivity. We don't have a high pH. Let's see. No, it's actually very acid, extremely acid. So it's not a salic horizon. A Pompeiic horizon, it's a buried, so it's not the case. An Arctic horizon, we just said that's not, because it's not possess any evidence of clay migration. The nidec horizon, it's a clay-rich subsurface, okay, that possess pressure faces, and we don't have any kind of shiny faces, so it's not a nidec horizon. Again, it's not a nargic, it's not a nidec. Spodic horizon possess a dark color that register alluvial concentration of iron oxides and soil organic matter. In this case, we don't have this because we don't have a dark color. Let's see. Here, we have a high huge and high value and high trauma here and here again. So we can't see any kind of evidence of concentration of dark materials. Okay. And the Ferhalic horizon, let's see. The Ferhalic horizon possesses a texture class of sandy loam or thinner and a clay content that it's equal or higher than 8%. So in this case, let's see. We have 62% of clay, so it's quite high. And we have a clay class texture it's thinner than sandy loam. So, okay, we are following this criteria. It possesses less than 8% of coarse fragments. We don't have any kind of information about coarse fragments in this materials, in this B2, B1, and BA horizon. So we don't have coarse materials here. So it's lower than 8%. We have a cationic exchange capacity divided by the clay content that's lower than 16. So let's see. In this specific case, if we calculate the CEC of the B2 horizon, let's calculate this. Is potassium, that's 0, calcium, magnesium, hydrogen plus aluminum, and sodium. So we don't have sodium and potassium. So in this case, it's just a sum of calcium, magnesium, and hydrogen plus aluminum. So it's 0.08 plus 0.04 plus 2.3. So this is the CEC in this case, the cationic exchange capacity. And now we need to divide this number by the clay content, that's 7%. So let's calculate this. And now multiply by 100. So we have, in this case, a cationic exchange capacity divided by the clay content that's equal 3.4. And it's lower than 16. So in this case, this criteria is followed too. It should present a low content of easily weatherizable minerals like feldspar, plagioclase, biotite, and other minerals. We don't have any kind of information about this, but we can consider that in this acidic pH and with this low cationic exchange capacity, we don't have a lot of easily weatherizable minerals.
Excuse me, JJ.
Yes, yes.
I thought we multiply with the value of clay instead of dividing.
No, we divide it because you can see here, it's the CIC by clay content.
Okay.
So you should divide, okay?
Oh, not multiply.
No.
Okay. Thank you.
Okay. If you multiply, all values should be higher. So we should process a ferralic horizon with a low clay content and a low CC to be lower than this. And actually, several or the majority of the ferralic horizon, they possess a high clay content, okay, because they are intensively wafered, and wafering produce clay, okay?
Okay. Thank you.
Okay, welcome. So we have a fine texture. We don't have a high volume of coarse materials, coarse fragments. We has a low CEC divided by clay. We don't have a high volume of easily weathable minerals. We do not have andic or vitric properties. These properties are related to materials that are formed by the weathering of tough and volcanic glass. And in this case, we should register some minerals, specific minerals, and we should register a specific pH, okay, a pH that generally is very high. So we did not have this kind of materials, and we are following the criteria. And the ferralic horizon should possess a thickness that it's equal or higher than 30 centimeters. So we have, in this case, just the B2 horizon, we have 14 centimeters. So we are following all the criteria to a ferralic horizon. So the B2 horizon is a ferralic horizon, and if we calculate and evaluate the B1, it's also a ferralic horizon. So we have the B2, B1 classified as a ferralic horizon, and so we have a hortic horizon in the surface, and a ferralic horizon in the subsurface of the soil, okay? These two diagnostic horizons could help us to classify the soil in this example. And what we start to do, we start to classify soils in the next class, okay? Using the classification of the surface and subsurface diagnostic horizons. So in this case, we have the ferralic horizon here, and here we have the ferralic horizon too. So we have, in this example, the hortic horizon in the surface and the ferralic horizon in the subsurface, okay? And let's see the last example. The last example, we also should classify the surface and the subsurface horizons. And the surface horizon possesses 25 centimeters of thickness. It possesses a red color because possess a a hue that's 2.5. So a low contribution of yellow and a high contribution of red. It possesses a low value and a low chroma. As we can see, it's equal or lower than 3. So it's very dark, made of dark red or brown red color, okay, maybe black, something like that, because we have a very low value and very low chroma. The structure possess a strong grade, so the pads, they are very stable. We have a coarse size and a granular type of structure. So this type of structure helps us to understand that it should present a good organic carbon content and or should possess intense bioturbation, intense biological activity. Okay. The consistency of this horizon, it's soft when dry, so can be easily broken. It's friable when moist, and non-stick and non-plastic when wet. Okay, and they possess a smooth and clear transitional to the other horizon, the B1 horizon. Okay, so let's check the physical chemical soil properties of this first horizon, the surface horizon. In this case, we possess moderately acidic pH. It's not too acid. The aluminum content, it's equal to 0 because we have possessed a pH that it's higher than 5.6. So we have a low aluminum content or equal to 0 in all the pHs or in all the horizons. I'm sorry. We possess a soil organic matter content that's low, it's not very high, and we can calculate, in this case, the organic carbon content. Let's do that again. So it's 1.6, and we should divide it by 1.724, so it's just 0.92. So it's not a high content of soil organic carbon. In this case, we can see that this surface horizon is organic horizon. It's not organic, it's mineral horizon. So it's not a histic or folic horizon. Okay. Let's see which surface horizon it could be. So it's not a folic or a histic horizon. And anthracic horizon, it not possess a gray color, so it's not a anthracic. A hortic, let's see, it should possess a high content of phosphorus. And here, let's see, the content is very low, so it's not a hortic horizon. Let's see here, a hygric horizon should possess a difference of texture between these materials because we have a fine concentration of fine particles in the surface, which could be identified a pelagic horizon. It possesses a relative high organic carbon and a low base saturation. Let's see, it should possess artifacts. We don't have artifacts. It should possess a high content of phosphorus, so we don't have also this high content of phosphorus, so it's not a pelagic horizon. 2, a pratic horizon should possess charcoal, bones, artifacts, or coal. We don't have any kind of this material, so it's not a pratic horizon. Thermic horizon, a thermic horizon should possess an additional of mineral and organic materials. So it should possess evidence of the addition of material, okay? It should possess a high base saturation and evidence of land surface a rised land surface. We don't have this specific information, so it's not a thermic. And we have right now a molic horizon that possess a high base saturation, evidence of high biological activity, dark colors. It should possess a strong grade, and let's see. We should possess soil aggregation with aggregates that's equal or lower than 10 centimeters. We don't have this information, but we can see here. Oh, I'm sorry. I'm trying to, this. We have coarse materials, coarse pads, coarse aggregates are not extremely coarse or very coarse, so they don't have a very high size. They could present a cloudy structure, okay, but one or the other. They should possess a soil organic carbon that's equal or higher than 0.6%. And we have, in this case, 0.9. So we have our organic carbon content that's following this criteria. Okay, we should possess a low value and a low chroma. And we have a low value and a low chroma. As we can see here, it's 2 and 1. And here we should possess equal or lower than 3, and equal or lower than 3. So we have 2 and 1. We are following this criteria. We should possess one of these characteristics if we have a calcium carbonate in the soil and we don't have any kind of material that suggests contribution of calcium carbonate, so we don't need to follow this criteria like the letter C, because it's this option or this option or this option. So if you are following this criteria and these criteria, the number 1 and the number 2, we already have a molic horizon. So in this case, we are following number 1, number 2, and number 3. 3, letter A. We don't need to follow B or C because they are OR. So in this exercise, we have a molic horizon and the surface. Okay, perfect. Oh, sorry. And now, again, here's some Portuguese words. I'm sorry. Here we have the B1 and B2 horizons, and now we need to identify the subsurface horizons. Okay, let's see. The B1 and B2 are very similar. They have similar color, and they have a slightly variation of structure. Here, strong, coarse, subangular block, and here, strong, small, subangular block. So here we have a higher or larger structure, but they are very similar. Here we have a hard consistency that's firm, slightly stick and slightly plastic, with abundant and clear shiny surfaces. Like here we also have abundant and clear shine surfaces. And you should remember, if we have shine surfaces, we always should think into specific subsurface horizons, the arctic and the nadic horizons. The difference between them is that the nadic horizon should not possess an increase of clay content in the subsurface horizon. So it not possess a substantial increase of the clay content in the subsurface horizon. And the arctic horizon, it could possess this kind of clay increase. It should possess an increase of clay content in the subsurface. Okay, so let's see. The clay content of the A horizon is only 32%, and the B1 horizon possess 49, and the B2 horizon possess 51% of clay. So it's a substantial increase of clay content. Let's see. If the surface horizon possess a clay content between 15 and 0.5% of clay, we should have a ratio between the clay content in the subsurface horizon and the surface horizon equal or higher than 1.4. So let's check. Let's calculate this. The clay content of B2 horizon is 51, and the clay content of the A1 horizon is only 32. So we have an increase of clay content of 1.59. 1.59, it's higher than only 1.4. So, okay, we are following the criteria to identify an arctic horizon. And just let us check if the B2 horizon and the A1 horizon have a distance equal or lower than 15 centimeters. In this case, the B1 horizon that are between the two, we have a thickness of, we have a depth between 25 centimeters and 42 centimeters. So 5, we have 17 centimeters of thickness. So in this case, we shouldn't calculate the ratio between B2 and A1 horizon. So we can't compare the B2 and A1 horizon, and the ratio that we calculate shouldn't be interpreted, and we should use the B1 horizon. It's because B1 horizon, it's too thick to allow us to compare the B2 and A1 horizon. So in this case, the B1 horizon has only 49% of clay content, and the first horizon, the A horizon, it's 32. And in this case, we have a very close value, 1.53 of ratio. So even when we use the B1 horizon, the increase of clay content, it's substantial. So we have, in this case, an arctic horizon in the subsurface, because we have shine surfaces and we have a high or substantial clay increase. Okay, so in this exercise, we have here anarchic horizon, stiffness. So we have in this example a molic horizon in the surface and an arctic horizon in the subsurface. Okay, we'll see in the next class how could we classify soil using this diagnostic horizons. Okay. 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 Very good. Very good. If you have a doubt, please let me know. If you did not find these answers, please, after the class, try to classify the material again, and I will share another exercise. So again, try to classify other materials to improve your ability to soil classification, okay? Okay.
Okay.
Okay. Okay, okay. So let's finish the materials. Just a moment. Okay, we finish here. We finished talking about Ferhalic horizon. Okay. Let's now talk about the vertic horizon. And the vertic horizon is a subsurface diagnostic horizon that's related to a high content of clay. So it always possesses a clay texture or a clayic material, a very high clay content. And these clays are composed by expensive clays. Say they can change its size, they can change the volume according to the soil moisture, according to the water content of the soil. And they usually suffer some shrinking and swelling process according to this soil water content. Okay, so in the dry season, when soil gets dry, they start to produce some cracks, some vertical cracks like this one, like these ones that we can easily see, that's related to the decrease of size, decrease of volume of these materials because they are losing water, so they are decreasing the size of the clay fraction. But when we have the wet season, when start to rain, all these cracks just disappear because the clays start to increasing its size because we have a lot of water between the clay materials, the clay layers. Okay, this variation of volume, variation of the size of the clays produce a lot of stress features, and we can see these stress features in the vertical horizon. Oh, here is just another picture that show you these cracks. You can see they are very large cracks. We can easily put our hand here, okay? And we usually produce a wedge shape of structure and prismatic structures like these ones. And here are these stress features that produce these shiny surfaces, but we can see easily these lines that are related to compression and stress between the pads, between the aggregates. So the materials, they are compressed between them, they are compressed against each one, and they produce these shine surfaces, okay? can see other shine surface here. It's quite easy to see because we can compare this surface here and this surface here, so we can easily see that in this surface we have a shine surface, and in this case this shine surface was produced by the shrinking and swelling process. The diagnostic criteria to identify a vertical horizon is that it possesses at least 13% of clay. So we can't see a vertical horizon that possesses a clay content lower than 13. It's not 10, it's not 25 or 29, it's at least 13% of clay because it's a clayic horizon, okay? And we should possess a high volume of wedge-shaped pads, wedge-shaped aggregates like this one that we can see, this V-shaped horizons, or V-shaped pads, I'm sorry, V-shaped aggregates, and or we should present silicon sites in a high number of surfaces in the soil aggregates. Silicon sites are these shine surfaces, like these ones. So it should possess stress features or silicon sites, okay? And it should possess a shrink swell cracks, like these ones, this vertical and huge cracks produced by the drying of the soil, okay? And the vertical horizon should possess at least 25 centimeters of thickness. So the vertical horizon is that horizon that possesses shine surfaces, and these shine surfaces are related to stress features. They are different from the other ones that we can see in the nidec horizon and the argic horizon, because the argic horizon, they are related to elevation of clay. So in the argic horizon, we should possess a difference of clay content between the surface horizon and the subsurface horizon. In the nidec horizon, we should possess a kind of blocky or polyhedral structures. And here we should possess a wedge structure. So it's a different size, or it's a different shape, it's a different type of aggregates. These aggregates, these wedge-shaped aggregates like these ones, are formed only in clay horizons that possess high activity clays, okay? And it should possess this planar cracks, this vertical cracks that are produced by the drying of the material. So the vertical horizon, it's not similar to nidec or ergic horizon because they possess different properties, different criteria, okay? Another horizon, another diagnostic horizon that's quite important is the natric horizon. And as the name says, the natric horizon possesses a high sodium content, okay? The natric horizon is a mineral subsurface horizon that possesses a high content of sodium and a substantial increase in clay content. This substantial increase in clay content is the same rules that we saw to argic horizon. So the natric horizon, it's quite similar to the argic horizon, but in opposite, the natric horizon possess an increase of clay content in subsurface due to increase of sodium in these environments. As you know, sodium is a dispersive element that can easily break the structures, easily break the pads, the aggregates, and once we have a high content of sodium, we can easily break the aggregates, we can easily break the stability of pads, and after that, if we have rain in this area, this clays that once was preserved inside the aggregates now could migrate through the soil profile and migrate from the surface to the subsurface. So the nitric horizon possesses an increase of clay content in the subsurface horizon due to the high content of sodium. This migration of clay is quite related to the sodium content because sodium content destroy the stability of pads, and once they are destroyed, rain and water could bring clay from the surface horizon to the subsurface horizon. Okay, so the nitric horizon possesses a substantial increase in clay content, but the mechanism of migration, of clay migration, is different from the Arctic horizon. The Arctic horizon is just a variation of volume that destroy the aggregates, and then the aggregates, the clay could migrate from the surface to the subsurface horizon. But here in the nitric horizon, we have a chemical influence of sodium. And as sodium is not available in high contents in all areas, in all sites of the world, we only can see nitric horizons in semi-arid and arid regions. So it's quite interesting that nitric horizons only can be found in areas that we have a semi-arid or an arid climate, because we can't register a high leaching in the sites, because a high leaching also could lost all sodium that have in the soil and could produce or help to produce or favor the producing of a nitric horizon. So we can see an Arctic horizon in several areas around the world, especially in the wet areas, in the tropical areas. But the nitric horizon we only can see in dry regions under a semi-arid or an arid climate. Okay. The nitric horizon, they usually possess a high density in the subsurface because we have an intense or substantial increase in clay content, and these materials, they usually fulfill all the voids. So we usually can't find a lot of roots like in this picture. We don't see a lot of roots in the subsurface horizon because we don't have high number of voids or huge voids, because all the voids, all the pores, they are fulfilled by clay that migrates from the surface to the subsurface horizon due to action of sodium. Okay, you can see this other picture in this nitric horizon, like in this picture, this is the nitric horizon, and here is the nitric horizon. These both pictures, we can easily see this horizon that possess an abrupt transition between the surface and the subsurface horizon. It's typically from the nitric horizon possess an abrupt transition. And because this high density, we usually can't see this kind of material with this kind of roots because they can't grow up and increase in depth, and they generally process this horizontal shape. And even in planar areas, we can see that water could migrate very easily because we don't have a high number of voids or huge voids. They generally are fulfilled by clay. So water migration is not so fast, it's not so easily, and generally produce flooded sites because this subsurface horizon that did not possess a high content of voids. Oh, sorry, I forgot to create to. Sorry, it's not working. Okay, I'm sorry. I just need to include in this case. So, okay, let me. Okay, and this. I'm sorry, guys. Here, okay, and in this case, just a moment. Okay, I think now it's working. Okay, good. The nitric horizon is a mineral material, as I said. It possesses a organic carbon content that's lower than 20%. It should possess a texture that's classified as loam sand or thinner and possess at least 8% of clay. And it's quite easy to understand why, because we are talking about a horizon that accumulate clay, so it should present at least 8% of clay and a fine texture, okay? And it should possess, if I compare the overlying coarse texture layer with this horizon, this nitric horizon, the coarser texture layer is not separated from the nitric horizon by a latex discontinuity. If you remember what is a latex discontinuity, is that difference of color, texture, structure that's related to influence of rivers or colluvium or alluvium materials or aeolical or glacial materials. Okay, so they are materials that was deposited in that area. They are not related to any kind of transportation, pedological transportation, or a pedological process. It's just the increase or the adding of material by the action of the geomorphological factors. Okay? If this coarser texture layer directly overlies the nitric horizon, its lowermost sublayer does not form part of a plot layer, so it's not formed by the human activity. It's not a human-made horizon, okay? Number 3, if this coarser texture layer does not directly overlie the nitric horizon, the transitional horizon between the coarser texture layer and the nitric horizon has a thickness equal or lower than 15 centimeters. So it's the same that we use to Argec horizon. If the coarser texture layer has less than 15% of clay, the nitric horizon has at least 6% more clay than this coarser texture layer. It's the same to Argec horizon. If the coarser texture layer has between 15.5% of clay content, the ratio of the clay in the nitric horizon to this coarser texture layer should be equal or higher than 1.4. Again, it's the same rule for the Argec horizon. Or if this coarser texture layer has equal or more than 15% of clay, the natric horizon should possess at least 20% more clay than this coarser texture layer. Again, the same rule for the arctic horizon. So you can see that all these criteria are the same for arctic and natric horizons because they both possess a substantial increase of clay content, okay? But we have some specific criteria to identify natric horizon. Let's see. We also can present as clay braids or clay coatings in thin section, as we saw in the arctic horizon. Okay, so again, it's the same. And they should present one or more of these criteria. It should possess a columnar or a prismatic structure. So let's see, this is a columnar structure that we have a vertical dimension that's quite higher or larger than the horizontal. And in this case, we have this convex top, and this is a prismatic structure that we possess a vertical dimension that's quite higher than the horizontal dimension, but the top it's very, very sharp, okay, and did not possess a convex shape. Or it possesses an angular or a subangular block structure and a penetration of an overlying coarser texture layer in which we have uncoated sand and or coarse silt grains extending at least 2.5 centimeters into the natric horizon. So it should possess wavy or irregular transition between this coarser texture layer and the natric horizon. And this horizon, this coarser texture material, should possess uncoated sand or silt grains. We should possess a high exchangeable sodium percentage that should be equal or higher than 15%, okay, in the upper 14 centimeters. Or we should possess more exchangeable magnesium plus sodium than calcium plus exchangeable acidity, okay, in the first 14 centimeters. And we should possess an exchangeable sodium percentage that it's equal or higher than 15 in some subhorizon that start below the upper limit of the natric horizon and in the 15 centimeters, okay? And it should possess a thickness of 1/10 or more of the thickness of this overlying mineral material, if present, and one of these two options, at least 7.5 centimeters or 15 centimeters, according the material that has. It possess a class of sand loamer and thinner, or if not possess this kind of texture. So we have some properties that are related, that's quite related, that are the same for the arctic horizon, that is substantial increase of clay content, or this features that express clay migration. But we have some properties that are particular from the natric horizon, that is a specific kind of structure like the A or B, and a high content of sodium or sodium and magnesium, okay? And of course, a thickness. we always have at least 0.5 centimeters to identify a diagnostic horizon. In this case, it should be 7.5 or only 15 centimeters. So let's see. Here we have an example. We don't need to worry about these names in Portuguese, okay? We just need to verify the content of sodium, and we can see, especially in the last soil profile, a high content of sodium. You can see here, and we have a high content of sodium, a high content of magnesium. Here, you can see the both. And if we calculate the saturation of sodium, the exchangeable sodium percentage here is 13%. So it's very, very high. It's higher than 15. In this last soil profile, this BTNZ2 horizon and BTNZ1 horizon, they possess more than 15% of cationic exchange capacity fulfilled by sodium, only by sodium. So they both could be classified as a natric horizon. In this example, the third example, the deepest horizon also possesses a high sodium saturation. And the first and the second examples, we don't have a high sodium saturation. So we should check the structure or other information to identify if they possess a natric horizon. But the 30 and the fourth horizons, soil profiles, I'm sorry, they possess a natric horizon. Other important horizon, diagnostic important horizon, is a plantech horizon. And the plantech horizon is a horizon that's produced by cycles of drying and wetting. So those horizons that are produced by periodically influence of water table or tidal water, or some cemented or dense layer that avoids or limit the migration of water and produce some reducimorph features like these ones, like the splintites that are concentrations of iron and or manganese oxides. So we can see in this photo, this gray color and these red dots that are oxymorphic features that represent, that express concentration of iron oxides in these dots, in these spots, and indicate to us that this horizon is periodic influenced by water, by the water table, for example. We also can see this kind of colors that show us that this horizon, this soil, was influenced in the past by the water table, but today it's typically from a well-drained area. But this recent past, favor the formation of a high content of plintites, a high content of oxic and reducimorph features, like this yellow and red masses of materials in this horizon. And so we can see this kind of horizons that possess more than one color, and these different colors are related to reducimorphic and oxymorphic features produced by the drying and the wetting of material, the variation of soil moisture regime. The plantech horizon is a mineral material, so it should possess a low content of organic carbon, lower than 20%, okay? It should possess at least 15% of area that express these oxymorphic features inside soil aggregates, and they should present black and redder colors, okay, than the surrounding material. So we should possess at least 15% of area that's covered by plantite, okay, by the concentration of iron and or manganese. In the areas that we can see only red or yellow colors, we saw that these materials are iron oxides. But when we saw dark colors like this area, like these dots, like these spots, we usually says that we have manganese oxides or iron and manganese oxides. So the plantech horizon should possess a high area that express these oxymorphic features. That's quite interesting because none of the diagnostic horizons that we talk about yet talk about these oxymorphic features. So the plantech horizon, it's very easily identify it in the field and even in an exercise because it possesses a high area of these oxymorphic features, okay? It should possess a high percentage of iron that's extractable by diatonite in the fine earth. It's because this kind of iron, it's quite related to well crystallized oxides. So we should present a high content of iron that's related to oxides, okay, oxides in this horizon. And it should present at least 10% of iron in these oxymorphic features that express the concentration of iron. And you can see that in these oxymorphic features where iron should be concentrated, you should possess a higher content in comparison with the fine earth in the areas that we don't have the concentration of iron, of course. It should be irreversibly changed when we get this material in a water cup, okay, because it was continuously cemented horizon, okay, or at least a strong cemented material that indicate to us that iron concentrate in that point and we have a high concentration of iron and these materials, these dots, these spots of concentration, they was exposed to drying and wetting cycles. And when they get dry, they start to get cemented. So they start to present a hard consistency or at least strongly cemented consistency, okay? It should present a ratio of iron oxalate and iron ditonite lower than 0.1 because this kind of iron is related to poorly crystallized minerals, and this kind of iron is associated, it's correlated to well crystallized oxides. So we should possess more iron associated with well crystallized minerals than these poorly crystallized materials, okay? And the plantech horizon does not form part of a petroplantic or a pisoplantic horizon. We'll talk about this horizon in the next slides, okay? So don't worry. And the plantech horizon has a thickness of at least 15 centimeters. So the plantech horizon is a horizon that possesses a high content of iron. This high content of iron is associated or is correlated with well crystallized minerals, and they express iron concentration spots because they was influenced by water in the past, but not today, and they cover a high area of that horizon, as we can see here. In opposition to the planitic horizon, the piezoplantic horizon presents a large concentration of iron and manganese, but now they are expressed as concretions or nodules. They are not anymore plantites, so they are not models or mass of material, but cemented materials, and they express a high and a large area of the horizon that's quite related to this cemented materials. As we can see in this picture, here we have several piezoplantic horizons, like here, 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 and even very close to surface, because we have a lot of these materials. We have a lot of iron concretions or iron and manganese concretions and nodules, okay? Just remember, concretions, they possess a particular internal shape, internal structure, like a layer, like layers, like an onion, for example, and nodules, they did not possess internal fabric. They did not possess internal shape, an internal organization of these materials. Like in this picture, we can't see here any kind of fabric, internal fabric. So in this example, it's a nodule, okay? And here we can see a high number of nodules in all horizons. So we have a lot of piezoplantic horizons, and we can easily differentiate the piezoplantic horizon to the plantic horizon, because here we have cemented bodies, and there we can have the cemented bodies, but the majority of them are only masses, are only material that start to get cemented, okay? Other example, here is another soil profile with a lot of coarse material, and these are not rock fragments, but iron nodules, iron concretions in a high number, in a high volume of these horizons, okay? And the diagnostic criteria of the piezoplantic horizon is it has at least 14% of the volume that's occupied by a single or a combination of concretions and nodules that possess a yellow color, a red color, or a black color. Again, yellow and red, they are related to iron concretions or nodules, and the blackish concretions or nodules, they are related to manganese or iron and manganese materials, okay? They could be related to fragments of a broken up petroplantic horizon. We don't know what is a petroplantic horizon, but we talk about in the next slide, okay? And possess a diameter that it's higher than 2 millimeters, okay? And the cementation class of at least moderated, cemented. It's not part of a petroplantic horizon. We could talk about this horizon in the next slide. And it also has a thickness of 15 centimeters. So the piezoplantic horizon, it's composed by a high number of concretions and or nodules, and they possess cementation class that express hard materials, and they are not part of petroplantic horizon. Okay, what is a petroplantic horizon? is a continuous or fractured layer of cemented material, like this one. We can see here a layer that was cemented by iron, and we hardly can broke this horizon with any kind of materials. Only heavy tools could easily break this horizon, because all voids, all coarse fragments, or all fine material is cemented by iron in advanced crystallization, and it's quite hard to break this material. So we can see from the plantec horizon to the pisoplantec and petroplantec horizon that the cementation increase and the porosity decrease. Here in the plantec horizon, we have a high porosity because this horizon was influenced in the past, in a recent past, by the water table or tidal water. So we have a lot of reduximorphic and oxymorphic features, but they are not so cemented. Here, they start to be cemented, and we increase the content of the cemented bodies, but they are not continuous. You can easily see some roots that could penetrate through this horizon because we have a lower porosity comparing with the plantec horizon, but we can see some voids here and here because we have a lot of voids between these coarse materials, these concretions or nodules. But here in the petroplantec horizon, we can't see voids anymore, or we only have a very few number of voids because all the material is cemented by iron and or manganese. Okay? In this horizon, we usually found very low soil organic carbon content because the biological activity here it's very low. It's very low because we don't have a lot of voids. So we don't have a lot of animals and roots increasing the organic carbon content here. In this picture, we can see here the petroplantec horizon again, and we can't see any kind of root here. And the diagnostic criteria to the petroplantec horizon is that is a mineral material, again, possess a low organic carbon content. It consists of oxymorphic features, okay, that forms these soil aggregates, and they possess this reddish, yellowish, or blackish color. They possess a high content of iron, especially in these oxymorphic features. And it possesses a cementation that at least is classified as strongly cemented. It possesses eventually vertical fractures, and these vertical fractures are not formed by the change of volume, but only by the cracking of the material. Okay, you should remember these materials has a lot of iron, so it could achieve high temperature in the day and a low temperature in the night. So we have some cracks that are formed by thermal desiccation of material. It not have coarse roots except if these roots are present in vertical fractures. So the petroplantec horizon, it's a layer, it's a horizon that it's very hard to use because it avoid the root growing, it avoids the migration of water, and it has a thickness of at least 10 centimeters. So the petroplantic horizon, as the plantic horizon, has a lot of iron, but in this case, this iron cement all the coarse and fine materials, and we don't have a lot of voids. The last one horizon that we talk about is the cambic horizon. And the cambic horizon is a horizon that could possess a weak to relatively strong developing. The cambic horizon possesses a distinct color when comparison with the parent material, but we can easily see several soil properties that are related to the parent material, because the cambic horizon comes from the word cambic, from Latin, change. So they are teenager horizons. They are horizons that are growing up, and they are getting different from the parent material, but they did not register any kind of specific soil process, like the concentration of iron or producing of stress fixtures or the increase of clay content in the subsurface horizon. So they did not possess any kind of specific soil formation process, only pedalization. So we can see pads, we can see aggregates, we can see specific color, and this color is different from the sea horizon or different from the parent material, but it's just that the B horizon did not possess any kind of other specific soil property. As we can see in this picture, here is the A horizon, and this yellow horizon, it's a B horizon and a cambic B horizon, because it possesses all the criteria to classify a cambic horizon. Okay? The cambic horizon did not possess any kind of clay surface features, so did not possess any kind of shiny surfaces, and did not also present any kind of substantial clay increase. Okay, so the clay content, of course, could increase. It's not a high increase, it's not substantial increase. And see here in this picture, between 0 and 10 centimeters, A horizon, and between 10 and 13 centimeters, we can see a dark red horizon that could be a transitional horizon, but between 13 and 55 centimeters, we can see here a horizon that possess some coarse fragment materials like here, and we can see some roots and some voids, and in field we can see any kind of soil feature beyond aggregates, beyond pads. So we can see a B horizon, but we can't see any kind of specific soil process, and it's why we are calling this horizon as a cambic horizon. We usually said that the cambic horizon is like a trash can. We can't classify that horizon in other diagnostic horizons, so that horizon turns on a cambic horizon, because the cambic horizon is that diagnostic horizon that hosts all the horizons that can't be diagnostic at other diagnostic horizon, can't be classified as other diagnostic horizons, because they did not present any specific or particular soil feature, okay? And the diagnostic criteria to identify a cambic horizon. They are mineral materials, so the organic carbon content should be lower than 20%. It should present a sand-loam or thinner texture, or a very thin sand, or loam and very thin sand. If we have a parent material that possess a lot of quartz, for example, quartzite, we could produce a sandy cambic horizon. But to produce this kind of horizon, it should possess a high content of very fine sand, because very fine sand help in producing of pads, of aggregates. If we have a high content of coarse sand, we usually can't see any kind of structure, so we can't see any kind of cambic horizon, okay? The cambic horizon should possess soil aggregates, so it should possess structure, and at least the half of that horizon, so we should possess a few moderate or strong structure. We can't see kind of massive or single grain structure in a cambic horizon. It should possess a subangular, blocky or angular blocky, or prismatic or granular, any kind of structure, but should be at least half of this volume of that horizon, okay? It should possess evidence of soil formation following one of these possibilities. Should comparating with the directly underlying layer, it's not separated from the cambic horizon by a lytic discontinuity, and follow one of these properties that present a color that's redder, so should present a more intense color comparing with the sea horizon or comparing with the parent material, because the cambic horizon produce and possess a specific and particular color, okay? It should possess a chroma that's equal or higher than 1 unit when we're comparing the underlying layer, and it should possess a clay content that's equal or higher than 4%, comparing with this underlying layer, okay? So it should possess a higher clay content than the sea horizon or the CR horizon. If we compare the cambic horizon with the overlying mineral layer, and it possesses 5 centimeters thickness, they are not separated by a lytic discontinuity, and it should possess, again, higher hues, higher values, and higher chromas, because the cambic horizon should possess specific colors that are produced by soil genesis, okay? Or if they are directly underlaying that did not present a glaic properties and not form a calcic or gypsum horizon, it evidences the removal of carbonates or gypsum by the weathering, okay? Or it should possess a higher content of iron, or even higher than 0.1%, and should present a ratio between iron that's related to poorly crystallized minerals that's equal or higher than 0.1 when we divide by the content of iron that's associated with well crystallized minerals. So we should possess a higher content of iron associated with poorly crystallized minerals, because this horizon is not so well formed. Remember, it's a teenager horizon, so it's not so developed as a ferralic or edgic horizon, so it shouldn't possess a high content of iron associated with well crystallized minerals. Okay, it should possess, as I said, high chroma and a high values, because it's related to a formation of color, different color from the parent material, and it not should be related to any of these horizons or layers, because it's not related to any specific soil process. So as I said, it shouldn't be related to a ferralic horizon or a vatic horizon or a pratic horizon or a molic horizon or a natric or a nitric or any one of these. So the cambic horizon is only presented in that soil profiles that did not possess a specific soil process formation, okay? And has a thickness of at least 15 centimeters. So again, the cambic horizon is that horizon that can be seen in some soils that are not so developed, but also are not poorly developed. Okay?
Okay.
Okay. People, after this class, we finish all the soil diagnostic horizons, and in the next class, we start to classify soils. So in the next class, we start to see how can we classify a ferro soil, how can we classify a hard soil on acrosol, and after that, okay? So please try to finish the reading of this diagnostic horizons. I will share another exercise to you all, trying to improve the ability of soil classification, and after that, we start the last topic of our course. Okay?
Okay.
Okay. So
Okay.
thank you very much, and see you on the next class. Bye-bye.
Okay.
Bye-bye.
Bye bye, JJ.